Hello, today we continue solving problems and tasks on the conservation of momentum and energy. A bar of mass 0.43 hundredths of a kilogram is attached to a horizontal spring with a stiffness of 20 newtons per meter. This bar can move on a horizontal surface without friction. A lump of putty of mass 0.5 hundredths of a kilogram is thrown horizontally into this bar with a velocity of 2.3 tenths of a meter per second. The putty sticks to the block. How much will the putty block system compress this spring? Let's think about what this question is. That is, how much will this spring compress? Well, objectively here, we understand that this is its deformation, i.e., the amount by which its length has changed. We will denote it in this topic as x, that is, it is its absolute compression. What do we have? The mass of the bar M1 is 0.43 hundredths of a kilogram. And the stiffness of the spring is 20 newtons per meter. And we also know that M2, which is the mass of the putty, is 0.5 hundredths of a kilogram. 5 hundredths of a kilogram. And it is also known that it was thrown at a velocity of 2.3, 3/10 meters per second. You have to think about it from the point of view that, first of all, the spackle has stuck to the block, so it set it in motion. And then the block starts to compress the spring. So we're looking at two things in sequence. The first is the impact of two bodies, and the second is the process of spring compression. Let's divide the problem into two parts. So the first part will be devoted to the collision of two objects. Let's draw this picture taking into account that the piece of putty moved with velocity v1, its mass was equal to v2, and the bar was standing still in this case, attached to spring and some apparently horizontal wall. This is how we can show this figure. There is no friction in the system. This is a very important point. We will speak about it later. The bar in this case stood still. Its velocity before the impact is 0. What happens after the putty hits this bar? The bar starts its motion with some velocity. So now both M2 and M1 have some velocity. Let's call it V2. And then this spring begins to compress. You and I will have to describe the impact itself, and we see that the two bodies after the impact have the same velocity. This indicates that the impact is inelastic. So for an inelastic impact, we know we're using the law of conservation of momentum. Let's write it down. So let's take the motion right away, taking into account the direction on the chosen axis. Here, the axis will be pointing in the direction of motion of all these objects. We can immediately write down this law in scalar form. So we get that m2vi is the momentum of the putty before the impact. For the bar, it is equal to 0. After the impact, we can see that these two bodies have a common velocity. So let's write that down as mi plus m2 and multiply that by some velocity v2. From this equation, we can see that the only unknown quantity here is v2, which is the velocity of this system after the impact. So by doing some simple calculations, we get a value for this velocity based on this formula. Let's put the value in and see what that equals. Speed. So m2 is 0.5 hundredths. 5 hundredths times its speed, 2.3 tenths, and divide by the sum of the masses. 0.43 hundredths plus 0.5 hundredths. 5 hundredths. So we get a value of 0.24 meters per second. That would be the velocity of the system, the putty plus this bar. Now, in order to determine how much the spring has compressed after the bar has started to move, we can use the law of conservation of energy, because now the energy of this system of these two bodies, the kinetic energy will be converted into the potential energy of the deformation of this spring. And at the moment of maximum compression of this spring, completely all the kinetic energy will be converted into potential energy. This is what the law of conservation of energy tells us. So let's say that the total energy of this system, kinetic energy, is the sum of both masses times the velocity of 2 squared and divided by 2. So the potential energy of the spring after the motion of these bodies is over is kx squared divided by 2. And given the law of conservation, we can say that the kinetic energy of the system has completely changed into potential energy. Now let's write down the expression. We see that here we can reduce the denominators, and from here we express the value for x. We get at once the formula m1 plus m2 multiplied by v2 squared and divided by k. So given that you and I are substituting values that you and I know, and with all the values here represented in C, so the value of this compression will also be in C. And after the calculations we get an answer of 37 thousandths in meters. If we translate this into centimeters, that is, we need to multiply by 100, and then we get 3.7 of a centimeter. The answer is also quite realistic, taking into account the given parameters of this problem. Muasat. This is the end of our lesson. Today we have seen how to solve the problem on the law of conservation of momentum and energy, which together can describe such phenomena. That's all. Goodbye.